Our next speaker is Deeparnab, and I do know that his setup works, at least it used to.
Can you hear me and can you see the slides?
Yes, perfect.
Great. Okay.
All right, very good. So the next talk is by Deeparnab Chakrabarty on faster Matroid intersection. And as before, if you have any question, please type it in the chat, and I will voice it. Okay, Deeparnab.
Okay, thanks. So thank you for inviting me to this great workshop. So I'm going to talk about this paper called Faster Matroid Intersection. The paper has 3 results, and I was deciding whether to sort of give a sample of all 3. Instead, I've decided to just give one result, and I'll mention what the other 2 results are at the very end. So this is a joint work with Intat Lee from Washington, Aaron Sidford from Stanford, Sahil Singla, who's currently at Princeton, and Sam Wong, who's currently at Microsoft Research. Okay, so I'm not going to assume anything about the familiarity with Metroids from the audience. So let's start with what Metroids are. So Metroids are this abstract setting of set systems which have beautiful structure and leads to efficient algorithms. So let me define them. So there's a universe V, and this V will have n elements. And there's a collection of subsets of V, I, which is the independent sets. And there are 2 properties that are satisfied. The first property is that if S is in the subset, then any subset of S is in the subset. So this is the downward closeness property. And in particular, the empty set is always there is always independent. The property that is important is the exchange property, which says that if I have 2 independent sets, and one independent set has bigger size than the other, so S size is strictly less than size of T, then there is an element in T, which is not in S, that I can add to S, and that S plus V remains independent. Okay, so this is if you've seen for the first time, this might be hard to visualize, but let me give the 2 paradigmatic examples of Matroids. So one is the following. So if you imagine your universe to be columns of a matrix, and any subset of columns which are linearly independent, they form a matroid. And you can check that the following 2 properties are satisfied. In particular, if you have a collection of vectors in a larger dimension, then you can always pick a vector into a smaller dimension, make it independent, keep independence. The other example, which many of us have seen in undergraduate algorithms, is if the universe is the edges of a graph, and I call a subset of edges independent if they induce a spanning forest, so there are no cycles, so that they are also form a matroid. They're called graphic matroids. So there are many other examples of matroids, but the problem that we are going to look at is that of matroid intersection. So let me state the problem. So the input is 2 matroids on the same universe. So VI1 and VI2. I1 and I2 are the 2 universes, 2 independent sets. And the goal is to output a subset which is independent in both matroids and has cardinality as large as possible. Okay. Again, the reason this problem is interesting is that it generalizes many problems. In particular, it generalizes bipartite matching in graphs. Here again, the V, this is always confusing. The V is the set of edges of the graph, and the 2 independent sets are so-called partition matroids, which basically constrain the degree on each side of the partition that the degree of edges picked is at most 1. So bipartite matching is one of the poster child applications of matroid intersection. There are many other applications, and one other thing might be finding arborescences or in trees or out trees interact in graphs. So, this is a problem that we will consider. And at this point, I should mention that how are we given these matroids? They're not given explicitly. So we're going to assume that we have access to an independence oracle for both matroids, which, given a subset S of elements, just tells if it is independent or not. Okay, and we're going to assume that this costs 1. Okay, and the whole talk will be concerned with how many queries are needed to this oracle to solve our problem, the problem of finding the largest common independent set. I should mention that although I'm not mentioning running times in this talk, it will be clear from the algorithm that the running time will be the same number of queries, that they're sort of going to be the same. So I've already said that the size of the universe is going to be n. The other parameter that one should sort of remember is r, and r is going to be the size of optimums, which is the size of the largest common independent set. Okay, so in particular, if you people know what the rank of matroids are, then the minimum of the rank is an upper bound, but r is the size of the largest common independent set. Okay, so that's the problem. That's matroid intersection. So let me sort of mention what was known. So this problem is a classic combinatorial optimization problem, and in a paper in 1965, Edmonds actually proved that this problem is polynomial time. And soon afterwards, there was a paper. The actual polynomial was pinned down to order nr square. So there are at least couple of papers which give this algorithm, and we're going to see this algorithm order nr square. And this was improved to nr to the 1.5 by Cunningham in 1985. And since then, this has been this was the best known result. Now note that r can be as big as n because or order n. So this gives an n to the 2.5 algorithm. So in a breakthrough result of 2015, subset of the co-authors actually gave this beautiful algorithm for cutting planes, and that implies an order n square log n algorithm. So what I'm going to try to show today is basically show that this order nr square algorithm of Lawler, we can give an faster implementation of it and get it to nr log r time. Okay, so oops, excuse me. Yeah, so again, this is an faster implementation of the nr square time algorithm. And in fact, one can say that this was probably missed, and concurrently and independently, Hui Guen from Northeastern also had a very similar algorithm. It has one extra log r factor. Okay, so that's going to, so this talk I'm going to give this nr log r algorithm in its entirety, hopefully. And one thing I should mention right away is that our algorithm works for the cardinality version. So I'm going to try to find a subset which has the maximum cardinality. One could look at the weighted version of the problem where every element has a weight, and I want to pick a set in the common independent set with the largest weight. We don't know anything better than, I think, order nr square. That's still the best algorithm, or n square, which is the Lee Sidford Young Wong algorithm. So Cunningham's algorithm, now algorithms don't work for cardinality. Okay, so I'm going to dive into the actually showing the algorithm, and this would be a nice time to ask any question if there are any. I see there are some action in the chat, but I have not been following it. But if there's a question, this would be a nice time to just ask it.
I think most of the action is a follow-up, basically
from the previous talk,
previous questions. Good. Okay. Sagnik is asking, what is known in terms of the hardness?
Okay, great. So almost nothing, but I'll lead to it in my last slide.
Good.
Okay, great. So here's the object. Okay, so my slides are. Here's the object that is of which drives the algorithms. So it's called the exchange graph. So suppose I have a subset S currently in which is independent in both matroids. So given this set S, here's a graph that I draw. So it has two sides. So there is a set S elements on the left, all the other elements on the right. I have a source small s and I have a source sink small t. And I draw the following edges. So I draw an edge from the source to a point X if adding X to S remains independent on the first matroid. Okay, so things that come into this V minus S set are going to be black in this dog and will be corresponding to the first matroid. So X is, I can add it to capital S and I can still remain independent. Similarly, I have an edge from Y to T to the sink if the same thing happens but for the other matroid. I can add Y to capital S and I am independent in the second matroid. Okay, so those are the edges that are incident on S and T. Otherwise, I have an edge from U in capital S, so something that is in my current set, to V, which is not in my current set, if exchanging U to V. So I take out U and I add V, and that exchange leads to another set which is independent in the first matroid. So this is a black edge, so this is independent in the first matroid. And I have an edge from V minus S to S, which is colored red in this talk, if similarly the exchange leads to independence in the second matroid. So if I take the element out from S, Q in this case, and I add P, then I am independent in the second matroid. Okay. So there are edges which are going into V minus S. You should think of it black, and they're related to the first matroid. Edges that are leaving V minus S, they're red, and they're related to the second matroid. And these if you're seeing for the first time, it's confusing, but this will help us build this small independence, common independence set larger and larger. Okay. So let's see why. Okay, so one thing should be clear. Let's see. So if I have a vertex V which is not in S, so that there is a edge from the source and an edge to the sink, which means that adding this V to the subset S makes me independent in both places. Well, then I should just add it. So finding a path of this form from small s to small t, from the source to the sink, immediately implies that I can do better. I can add this V to my set, and I can get a bigger independent set. Of course, there may not be such a V. Okay, so in particular, this is capturing all the maximal in common independent sets, and I might be at a maximal, S might be maximal, and there may not be any such V. So the second thing to note is, and this is sort of taking cue from maximum flow or our bipartite matching algorithms, that, well, what if I find a slightly longer path from smallest to small t? Okay, so let's say, suppose there's a path which goes from S to V to W to X to T. Okay, so it has all these meanings. One idea here would be, well, I should take out the things in capital S that I meet, and I should add the things in V minus S, and hope that this is independent in both sets. So in this picture, I take out W because W is in capital S, and then I add this V and X. And the question is this independent in both subsets? And again, if you've seen this for the first time, you think will be, why should this be independent? And indeed, the answer is no, as in it is not necessarily independent. But the cool thing is that if this is a shortest path, so if I take any shortest path from S to T, then if I do this augmentation, take out the things in S and add the things not in S that I meet on this path, then it is indeed going to be independent in both sets. Okay, so I'm going to just show why this is the case, because I think this sort of explains why this graph is there in the first place. So let me just show to you that if I do this augmentation, I take out W and I add V and X, why am I independent in I1? Okay, and the I2 will be similar. Okay, and the reason, and you'll see why shortest path comes in, is the following. So let's see what it means that SV is an edge. It means that S plus V is in I1. That's the meaning of that edge in the graph. And the edge WX means that if I take out W and I add X, then also I'm in I1. So I have these two sets which are independent in the first matroid. And you see that one set has bigger number of elements than the other. S plus V has more elements than S minus W plus X. Which means what? Well, from the exchange property, it means there is some element in the bigger set which is not in the smaller set that I can add to the smaller set and maintain independence. Well, the only elements that are not in the smaller set but in the bigger set is V and W. Okay, V is new and W has been kicked out. And we are claiming that we can add V. Why is it that I cannot add W? Well, and this is where the shortest path comes in. If I add W back to S minus W plus X, I get the set S plus X. But S plus X is not independent. Why? Because if it were independent, then there would be an edge from S to X directly, and I would have a shortcut from S to T. But I'm assuming that this path is shortest path, and therefore the other thing, the S minus W plus X plus V, should be the thing that is independent. Okay, so this sort of gives a flavor of why shortest paths lead to augmentation. If I augment along shortest paths, I'll get better and better in common independent sets. And in fact, this is the main theorem of Edmonds. or you can derive it from the theorem of Edmonds, which captures the duality between or certificate for optimality. So if I never have a path from, if there's no path from S to T, then I can stop and S is an optimum set. Okay, so this actually implies the following polynomial time algorithm. So if nothing, if you've seen this for the first time, this is already a thing that you should take away from this talk. The algorithm is just this: you start from the empty set, you construct the exchange graph as I described, find the shortest path, augment, and then go back. Okay, and you stop when there are no more paths. How much time does this take? Well, let's imagine what the exchange graph. There are R vertices on one side, at most R vertices on one side, because R was the maximum size of S, it's the optimum, and N minus R on the other side. The number of edges is N, at most N times R. Each edge I can, it takes one query to find. So that's order NR queries for step 2. Step 3 that doesn't take any queries. I just have to find the shortest path. And how many times will I do this? This while loop will run, so to speak. Well, every time I'm increasing the size by 1, the maximum size is R. So there are R augmentation. This gives me an NR square query algorithm. So this was the algorithm of Lawler, which hopefully is clear. Again, if there is any question right now, before I go to what we did, this will be the right time to ask. Okay. So our contribution is actually a better implementation of the above algorithm. And we'll basically say that the step 2, which is almost everyone, if you have followed this talk so far, step 2 seems very wasteful, that every time we are constructing this whole graph from scratch. And what we will show that we really don't need the whole graph, right? What we need is a shortest path from S to T. So if we can find the level set, so if we can find which are the vertices at distance 1, which are the vertices at distance 2, distance 3, and so on from the source S until I reach T. Basically, if I can do a BFS on this graph without computing the whole graph, then I'll be in business, right? So that's sort of the main idea. So the step 2 prime is what I'm going to get into next, construct the distance level sets. And then if we do that, then we can find the shortest path and repeat the same algorithm. Okay. So definition. So I'm going to say Li is the set of, so again, S is fixed. This is the exchange graph. And Li is the set of vertices which are at distance exactly I from S. So just to make sure we are all on the same page, the odd Lis, L1, L3, L5, are subsets of V minus S, because this is sort of a bipartite graph which alternates. And the even subsets, even Lis are there on this subsets of S, my current S. Okay. If we knew these, right? If someone only gave us the subsets and not the edges in between, then it's sort of easy to find a shortest path by just walking backwards from T. So T knows that it has a neighbor in L5. So it will just go and query every vertex in L5 till it finds a neighbor. That vertex will go and query L4 and so on and so forth. The number of queries will be at most order n, because every vertex is asked at most once. So this will take order n queries. Okay. Again, there are R rounds, order n queries per round, order nr. That's in our budget. That's not a problem. So let's forget about 3 prime. The problem is now how to find these level sets in a more efficient way than just taking the whole graph construction. Okay, so that's what the problem boils down to. And the main idea is, there are 2 ideas here. One is just using binary search. Okay, so let's sort of, this next slide is sort of the most sort of aha slide, that aha observation of the whole talk. So here's the setting. So I have S on the left, V minus S on the right. And suppose I give you a vertex V which is not in my current S, and let Q be any subset of vertices in S. And I want to ask the question, is there a neighbor of V in Q? Okay, so is there a W in Q so that VW is an edge in the exchange graph? So the main observation is that this can be done without having to query all the points in Q, but rather just doing a binary search and have an order log R query algorithm. Okay. Why is this the case? And this is the sort of the observation that, so let's see what it means for, suppose there is a W here and there's an edge VW. Well, if you remember, this is an edge, red edge. So this edge is there. If I take W out of my set S and I add V, this thing is independent in the second matrix I2. Okay. So I want to find whether such a W exists. And here's the reason. If instead of taking out W, if I take out all of these vertices in Q, okay, so I really take out a lot of vertices in Q and then I add V, and I find that that thing is independent. Well, then there must exist a single vertex W, which, so that taking out W and adding V also makes it independent. Why is that the case? Well, this also follows from the exchange property of matroids. Okay, so suppose there are 10 elements in Q and I took out 10 elements and I added V and I remained independent. So that's one independent set. And S is another independent set. So this means, the exchange property means that from S, I can keep adding elements to this S minus Q plus V and remain independent till the size becomes the same. So the last thing that I'll add will give me this W, so that S minus W plus V is independent. Okay. So that's the sort of the main observation, that if I, and sort of known, that if I take out the whole Q and see if it is independent, then I know that in Q there is an edge. And just to find that edge, so suppose now I have to find that edge, then the binary search will work, right? I arbitrarily partition Q into Q1 and Q2 and ask the same question. S minus Q1 plus V is independent or not. If it is, I throw away the other half. I can just fix on that half. And this says that getting an edge from V on the right side to Q on the left, whether there's an edge or not, and if there is, find it, that can be done in log R queries. So, the issue is, and I'll mention it again in the next slide, there is symmetry here. I cannot do the same thing for a V in capital S and Q on the other side. Okay, and the reason is that thing would imply that is there's a W in Q where adding W and deleting V is independent or not, and the same procedure of adding everything and asking if that is independent does not work. So that's the reason. There's an asymmetry here. This algorithm works only for edges that go into Q. Okay, so again, so this thing can be done in all log R steps, and the corollary of this is, if you give me, suppose I want to find out all the layers L1, L2, L3, and so on. If I've figured out the layers L1 to L2, okay, and I want L1, L2, L3, so this is as the picture shows, and I want to figure out the next set L4, then this is just, since I can figure out for every vertex in L3 what is the neighborhood in L4 using log R queries per vertex, I can do standard BFS thing and I can discover the whole set of L4 paying order log R for every vertex in L3 union L4. Okay. So if this thing, again, to mention the same thing that I said last time, if the same procedure of discovering edges was also true from left to right, then I would be done. I would find the sets L1, L2, L3, L4 paying order n log R queries. And then there are R rounds, and so I'll get order n log R times R. But there is an asymmetry, which brings us to the sort of the second idea of the paper of this result. So I could discover odd layers, even layers. Now, how do I discover odd layers? So suppose I have found L1, L2, L3, L4, and I want to figure out the neighbors of L4 in this thing below the line, right? So here's what we do. For every vertex which are below the line, every vertex which is undecided, which has not been assigned a layer, by using a similar binary search idea, I can find whether or not there is some vertex in L4, because L4 is in the S set, is in the nice set, whether there is an edge from that vertex to V. Which means that if I go and query every vertex below the line, paying order log R queries per vertex, I can discover L5. Okay. What's the problem here? The problem here, the same vertex will be asked again and again and again. Okay. But nevertheless, we can say the following: a vertex V in the V minus S side, how many times is it asked whether you are in L5, and next time whether you're in L7, and so on? Well, it is asked delta v log r times, where delta v is the level that is finally assigned to v. Vertices that are in L1 and they, which are found in the first step itself are never asked this question again. But the vertices that will be in L19 will be asked, 19 by 2 times, whether you are my neighbor, whether you're my neighbor, whether you're my neighbor, and so on. Okay, so delta v potentially is large, and this sort of does not give us what we need. We would like to have this order log r on its own. So the final observation here is that this is why everything works out is sort of the thing in amortization will be actually fine. And for this, we need one last observation, and this is okay. So maybe I should maybe the whole algorithm is this: I construct the level sets as described, and the problem is again in the odd level discovery. Even level discovery takes n log r time, but the odd level discovery, I have to pay this. Every vertex might pay many times this log r. So here's the final thing in the story which makes the algorithm work, is that I find an augmenting path. So I have a S, I find an augmenting path and I go to S prime. The graph can look, the graph, exchange graph GS and GS prime can look different, but there is some structure. And this was actually proved by Cunningham in his 1985 paper. It says that if S is augmented via shortest path in the exchange graph to get a new candidate S prime, then in the exchange graph, new exchange graph, the level sets, the distances can only increase. So for example, the picture on the left here is the exchange graph which I have with S, which has these level sets. And then I find a shortest path, augment, get S prime. S prime is S plus augmentation. And I look at the new level sets, L prime 1, L prime 2, and so on. The vertices can only go down. So a vertex in L1 can only be in L prime 1 or L prime 2 and so on. But a vertex in L3 cannot go back to L prime 1. So the vertices sort of trickle down in this layers. So this is what the monotonicity implies. And why is this good for our algorithm? Well, this is for odd level discovery, here's what we do. For every vertex not decided so far, they were in their some older L, so this vertex, it's in an older L5 or an older L7 and so on. So when I want to find the new L5, I can restrict my attention only to the older L5s. I don't need to ask a vertex in older L7 whether you are in new L5 or not, because monotonicity says that the old L7 will only be new L7 or higher. So the number of vertices queried is only the size of older L5, which means if I look at it from the right-hand side, every vertex in the V minus S is asked whether you are in the new, whether you are my neighbor or not, delta Vi times, where delta Vi is the difference between its old level and the new level. So for example, this vertex V, if it's asked whether you are my neighbor by L4, and we find that the answer is no, then this vertex V will move to L7, and maybe it again finds the answer is no, it'll go to L9, but the number of times that we'll ask this question is going to be 9 minus 5 if it ends up in L9, or 9 minus 5 by 2. So order, the difference of these things is going to be the number of times a vertex is asked, are you my neighbor? Okay, so that's the second observation. And so if I think about it, any vertex V across the whole R iterations, how many times is it asked from the right, are you my neighbor or not? Well, its distance at the before the algorithm starts, maybe it was 0, to its and the different distance at when the algorithm stopped, which is at most R or 2R, because the maximum distance is at most 2R in this graph. So the sum of these distances is order R. So amortized, I'll get order n log R. So to sort of complete this whole picture, even level discoveries takes n log R time per iteration, and there are R augmentations, so that's nr log R. For the odd level discovery, I'm going to do amortized over all these 4 steps. And I basically get log R times this summation, the number of hops, and this summation delta Vi is order R. So per vertex, it's order R log R. There are n vertex, so that also gives an nr log. Okay, so that's sort of I think the full algorithm for discovering, for the nr log R algorithm for finding the Matroid intersection. So I'm not sure how much time I have, but Michael?
think perhaps 1 minute.
1 minute. Okay, so let me then not. So I wanted to show why this again. This why should this monotonicity hold in this exchange graph? So let me skip that. Again, the proof is not that difficult. So let me sort of at least tell what the other two results are in the paper, and then conclude. So the most technical part of the paper is actually the following result. It says that suppose I don't want to find the exact, I don't want to solve this problem exactly, but I want a 1 minus epsilon approximation. Can I do better? So note that the current exact algorithm takes nr log r time. R can be as big as n, so that's a quadratic time, n squared time. Can we do subquadratic? So the main result is that you can. So the running time that we can achieve is n to the 1.5 times some polynomial factors in log n and 1 over epsilon to get an 1 minus epsilon approximation. And the main idea behind this is actually, instead of doing one augmentation at a time, if you're aware of bipartite matching algorithms, the first idea would be think, well, I should try an Hopkoff-Karp kind of idea of doing many augmentations at the same time. And indeed, Cunningham's algorithm does follow this flavor, except it's not the same. As in, if I make one augmentation, the graph completely changes, and it's not clear how to do parallel augmentations. So one of the conceptual contributions of our paper is this idea of what is called augmenting sets in the paper, but I like to think of them as augmenting highways. So instead of finding one path, we actually want a collection of these sets augmenting. So they look like they are highways with various lanes. It's not the same as parallel. I'm not doing parallel paths. I'm just trying to find these objects which are not a single path, but just a collection of subsets of various things, and then try to augment them. That thing we could do, except the algorithm is not as clean as we want. The algorithm works for a while, and then at some point we have to swap to single path augmentation, which is exactly what Hopcroft-Karp also does. So that part is more technical, and it's a part of a different talk maybe. So that's one result. The other result is that suppose I have a stronger oracle, which is the rank oracle, which says given a subset S, what's the size of the largest independent set? Then we can actually get n square root r query algorithm. In fact, we can implement Cunningham's algorithm. So let me stop with the question that was asked by Shagnik, I think, lower bounds. So these are oracle models. So we should be able to, there's a hope to prove lower bounds in this model, but there is no lower bound known for, there's nothing better than omega n. So small omega n is still open for finding a Matroid and so solving Matroid intersection using independence.
Is this for the number of queries to the oracle?
Yes, number of queries to the oracle, to the weaker oracle of the independence independent set. And really, we don't know much. I think the answer is, the exact number might be some, it's not even 2n if I'm not wrong. So so it's like 100n will be also interesting. So that was all that I wanted to say. Thank you for attention.
Thanks, Deeparnab, for the great talk. So Sagnik asks, is there a better if there's a better upper bound in the oracle complexity model? That is, what if you don't care about runtime?
So no, as in nothing. So this is the best known. I have not talked about runtime. So it also happens that our runtimes are also good, but this is the best algorithm known for even in information theoretically.
What if you were to what if you were to specialize this to say bipartite matching? So what would be the runtime?
So okay, it would not be that great, no? As in, because so
cubic seems clear, I think, right?
So there are two things here. So are you asking? So let me just clarify the question. The question is number of queries to the oracle, or how much time does it take to implement the oracle?
The runtime, yes, the total runtime. Maybe you can amortize, I imagine, right? That is I'm curious, basically, do you call the oracle on completely different matchings? That is, do you use long augmenting paths in the process? So how does the matching change?
So this is a good exercise, and what does this algorithm mean on a bipartite graph matching, right? And it is not quite clear that it is going to be the Hungarian algorithm. At least to me, it is not clear. So whether we could do an amortization is not, I don't know, I have to think about it, but it's a good question.
So Sepper is asking, basically, what is your belief on the right answer for the number of?
I would be very surprised if this can be done in order n.
I see.
But I don't have any very strong beliefs. Yeah.
Okay, good. And Jens is asking why the Hopcroft-Karp algorithm gives you only an approximate solution. Okay, so I guess your statement was that it does give you approximate solutions in the meantime.
So I did not explain the algorithm completely. So we, after a while, we have to give up on the augmenting sets kind of thing. It doesn't work. So this is not a good answer, but I've not explained the algorithm at all. The augmenting highways or so. So Hopcroft-Karp Cunningham's algorithm does not give approximate; it gives exact. But and in particular, Cunningham's algorithm. Okay, so maybe this answer will satisfy. So Cunningham's algorithm, or even Hopcroft-Karp in the matching case, gives a n by epsilon. So if you want epsilon approximate, then you can get away with n by epsilon. N times r by epsilon queries instead of nr root r. So you can get a better bound on running time, a square root r improvement, if you are okay with epsilon. And the reason is, again, I will stop as soon as the length of the augmenting path goes more than 1 over epsilon. So you could get an exact algorithm for our approximate thing, but it will take us to more than n square, and it will not give us anything better. Does that answer your question, Jens?
Yes, I believe so. Yes. Okay, great. So let us take the rest of the questions on Slack. So we have a Slack channel, so we should use it. And thanks again to all the speakers of this session.
And we meet again at 5:30 for the last session of the day.